All right, so we are now getting into chapter 4. We've talked about sort of the first part of chapter 4, where we were discussing the intro to the Lagrangian formalism. We talked about what Lagrangians were, how they functioned. We talked about the principle of least action, which led to this idea of, or which led us to this idea of the Euler-Lagrange equations, where I said if you're interested in actually looking at a derivation of the Euler-Lagrange equations, then you can visit my Patreon page, because that's something that I think is a little bit more busy work, if you will. But again, it's essential to know, and you can find it all over the place online. But in order to preserve time on this playlist, I thought maybe if you're really, really interested in me deriving the Euler-Lagrange equations, then what you can do is, you can just go into my Patreon page and look at that. Again, if you like these videos, you can hit the subscribe. That would be great help to me. Any contribution you make on my Patreon page will go into making these videos higher quality, where I can get myself a mic, or where I can actually, but I don't really have an office yet. I'm sort of working out of my dining room right now, and hopefully with any possible contributions that you guys can make, you can any of that will go to making these videos much better quality, at least. So let's get right into today's topic, which is Noether's theorem. So I've thought about Noether's, how I want to conduct this video. Again, a lot of this is going to be, like I did with the Lagrangian, like I did with the Euler-Lagrange formula, where I said, the Euler-Lagrange, deriving that's commonplace. And so if you want to see it, you go onto my Patreon page. Similarly with what I'm going to tell you now, if you want to see derivations of what I'm going to say briefly, then again, I think you can go into my Patreon page, because again, this is kind of commonplace. You should know this already, and if you don't, you can find YouTube videos on it. So I don't want to waste my time on the playlist section of this, at least, diving too deep into classical fields, because I think if you want to get to quantum fields quicker, then telling you that this is just the way it is for right now, it will get us there quicker. But if you don't want to accept that, which I don't recommend you do, I would go on to perhaps a different site where you can find derivations, or you can go onto my Patreon page where you can find derivations of these claims that are being made. Disclosure. Okay, so now let's get into this. There's 3 points that are going to be made about Noether's theorem. So Noether's theorem basically says that we have this Lagrangian. It's our fundamental field theory, and it's predicated on this idea of it exists in phase space, right? In phase space, what you have is your coordinate axes. I'm going to draw this as if we're looking at this head on, so this might be a little bit easier to understand. So I'm going to draw our field in a little bit of a different way. Here is our actually, no, I want to do it the other way, because I think it might be a little bit easier to understand that way. So here is our phase space, right? So we have our x's, actually instead of x, I'll do q's. So here's our q and our q dots, and this is the value that a Lagrangian is going to take. So again, this is a field, and the idea here is that tied to anything you do to this underlying Cartesian system, tied to anything that you do here, it's going to be, there's going to be some invariant quantity that's going to be associated with any rotations that you do to this Cartesian system. So let's break that down. If I were to rotate the system, any rotation, associated with that, the invariant quantity that comes out of our Lagrangian when we do that rotation is going to be angular momentum, right? So if nothing changes, so how do I want to do it? If we do this rotation, if we do this rotation, so I'll just say rotation, and nothing about our and nothing changes within our Lagrangian, then that means there's a conserved angular momentum. So conservation. Okay. If we shift our system, right? So if our new system looks like this, I'll just draw a different one over here. Sorry, I got something in my eye. Q and Q dot L. If we shift our system, right, to look something like that maybe, and nothing changes, so we have a shift. So that's a spatial shift, then we're going to get momentum conservation, or linear momentum conservation. So what I'll write here is shifting corresponds to momentum. Conservation. And then if we do this shift, which I can't really depict on our Cartesian system, but if we do, if we take time and we shift it over by some epsilon, some small unit of time, then this is going to correspond to energy conservation. Again, this all hinges on the fact that if nothing changes in our Lagrangian under these types of shifts, then we have a conserved quantity. Okay? And that's good. That's extremely important. That's what Noether's theorem is. Noether's theorem basically says there's a conserved quantity associated with different types of, there's a conserved quantity that's associated with shifting in your system, right? So if you rotate your system, you have angular momentum conservation. Or let me reword that. If you rotate your system and nothing changes in your Lagrangian, then you have angular momentum conservation. If you shift your system spatially, then you have momentum conservation, and if nothing changes in your Lagrangian. And if you have if you do a temporal shift in your Lagrangian and nothing changes in your Lagrangian, then you have energy conservation. Okay? So that's what these look like, sort of within our phase space. Again, time doesn't really exist in our phase space, like we said, but again, Q and Q dot are functions of time. So there's some leeway there. So that's Noether's theorem. Now what we're going to do is we're going to take this idea of Noether's theorem, and like I've said, if you don't want to take this on face value, then you can go onto my Patreon page where I will cover derivations of each one of these claims. Okay? Because again, I don't feel comfortable giving you this just straight up. Like this, it's actually like an itch for me that I want to scratch. But at the same time, I am telling myself, I know you guys want to get to quantum fields quicker. I know you guys want to get through the book quicker, probably, to be able to understand the essentials of quantum field theory. And so I'm telling myself, I'll put this on my Patreon page where you guys can check that out later if your heart so desires. But what we want to do now is we want to consider a shift in our Lagrangian. Based off of these claims that we've made, what does something like this look like? Well, we can start off with our field. Okay. And we have our x mu right here. Now, upon shifting our field, x mu shifts this way. Okay, and we end up here with this prime right here being our new shifted value. Okay. So what does this look like mathematically? This looks like, oftentimes you'll see it written like this. X mu gets transformed into x mu prime which equals x mu plus a small change in x mu. So I'll break this down again because you'll see this notation in the book and elsewhere. X mu gets shifted to x mu prime. So prime is the new coordinate. No prime is the old coordinate. The new coordinate equals x mu plus some shift. Right? So this is what this notation looks like. Similarly, we can do this with the value on that field. Right? So we have the field. We're shifting just points on the field, but the values on that field look the same way, right? So suppose we're dealing with a scalar field. So we have something that looks like this, gets shifted into a new value, which equals x mu plus a shift in our value at x mu. Okay. So mathematically speaking, that's what these look like. Okay. So what can we do with this? If we consider our Lagrangian again, if we take we can take the difference between our new Lagrangian minus something gets us our old Lagrangian back, right? There's So the shifted Lagrangian, so I'll do this. So L shifted. And again, this is a function of our values and the derivative of our values. And of course, the underlying field. That's one too many parentheses. Minus something. I'll just put something in here for right now. It's going to give us our unshifted Lagrangian, which is and this is actually fun. These are all primed, right? Our unshifted Lagrangian like this. So what is this something in here? Well, this something is going to be, bear with me here, I'll write it down. So it's going to be dl d phi. Okay, so this is the first term because we want to take the change in the Lagrangian with respect to the values. Okay, times the change in the values. And plus the Lagrangian is also a function of the derivatives of those values. And that's going to be changed in the derivatives of the values. Phi, like that. And then we're going to have our Lagrangian, again, of course, is a function of x mu, dx mu, right? So this something is this. Okay, and we're calling this the overall shift in the Lagrangian. So the overall, I'll go over this again. The overall shift in the Lagrangian is, because it's a function of three things, we need to take into consideration how it changes with respect to those three things. And those three things are the position, again, the values, the changes in the values, and the arguments that those values depend on, which are these guys. Now this is important because this thing here corresponds to what we're calling space-time symmetries, as opposed to internal symmetries. Internal symmetries are just going to be associated with this change right here. So because we have this added term, this is what's called a space-time symmetry, or space-time change, actually, and not a symmetry. Because we're changing this right here. That this is a change in the space-time, not a change in the values that are functions of the space-times. Okay, that's going to be an important note because there is such thing called space-time symmetries, right? And then there's going to be these things called internal symmetries. Internal symmetries are modifications in the field itself, right? So that's going to be these guys right here. These correspond to modifications in the field itself. This corresponds to modifications within the field, so like rotations and translations and stuff like that, right? So again, we have space-time symmetries, which we're going to be dealing with in this video, and then in the next video, we're going to be talking about internal symmetries. Okay. Okay. So now that we have our space-time symmetry change, say now we do this shift. Say now we do a shift here where we say that, actually, wait, no, before we do that, I will write down, so here is our change in our Lagrangian. Again, I'll just rewrite it, is equal to d phi minus, and because we had that minus sign right here, all of these are going to turn into minus signs, right? So we'll have minus dl d mu phi times a change in d mu phi's minus dl dx mu dx mu, like that. So that's our change in our Lagrangian. What we can do now is we can recognize that this here is really just a derivative of our, based off of our Euler-Lagrange equations, dl d mu phi, like that, and then times our d phi, like that. We want to keep everything in parentheses just to make sure we know what we're doing. Minus, again, dl d mu phi. And you might see where we're going here. And then still we have this dl dx mu x mu, right? Now here, this is the important point here. This is one of the punchlines of this video, is that this here, this right here, this is chain rule, I believe. I'm trying to remember my names in calculus. This is going to be, so you have your product rule and your chain rule. This is actually the product rule, I think. So, and you could see that because we have a derivative, we have a change in this right here, and then we have a change in this, which is right here, right? So what this ends up looking like, if you can follow me, is that d mu of, again, this is kind of like the inverse of the product rule. Yes, the product rule. Like that. Right, because we can actually interchange this guy here, these two guys. I'll make it look like this, because these are just changes. We can actually interchange those like that. And so what we get is something that looks like this. You can look for yourself. If you do the derivative of this, you have to do the derivative of this times this plus the derivative of this times this, and you get this. And then we get our good old dl dx mu x mu, like that. And what we can do now, again, or not again, but what we can do is we can say that, again, this is our change in L. And if we make our shift now, we haven't really made the shift yet. We said that this is the rule for the shift. So let's make this shift now. So if we make the shift, then we get that dl is equal to d mu dl d mu phi d phi minus dl dx mu. I'm going to put a mu right here because I'm going to say that x mu is equal to x prime mu is equal to x mu plus a mu. So our small change, the small change in our shift is going to be this defined by this little vector. All right, so the vector is the degree to which we've shifted. Okay. And that means that phi prime is equal to phi minus d phi dx nu a mu. And the reason I'm putting nu instead of mu is because I don't want to copy any dummy indices. Usually when you're putting dummy indices down, you want to put as many as you can down so that you don't do any reiterations, because you want to take into account even combinations of those. Not even, as in even or odd, but you want to take into consideration all of the possible combinations when you do this. Again, this is a sort of a rule in putting dummy variables in, because you don't want to leave anything out, basically. And so what this means is that we can put this in for our d mu, because that's our d mu. This is our change, right? So I will just do that right here. D mu dx nu a nu, like that. And we end up now, this video might be a little bit longer than 30 minutes, because I realize we're pushing on 30 minutes right now. So maybe it might be 45. We'll see. And well, because that was a minus, because this was a minus sign, we can actually get rid of this minus sign right here. So what we're left with now is d mu. I'm just going to put this more concisely. dl like this, d nu phi, phi a nu, because the reason that's an upper index is because the values are values, right? So you need to have an upper index contract with a lower index to get a number. I believe I talked about that earlier. I can't remember though. If you have two lower index values, then you don't get a number out of that, right? If you want to get a number, you need an upper index value to contract with the lower index value. That's something I either would have covered in my first or second videos on the special relativity, when we were talking about our non-trivial space-time structure, right? We wanted an upper index with a lower index to contract to give us a number, right? The number associated with some distance. Right here, we need to contract to a number because we're looking at values in the field. So similarly, we would do the same here, where we have d mu L A mu, like that. And so what does this end up being? Well, this ends up being, we can take out our d, so we have our d mu, and we have this part, like this. And so what am I going to do? I'm going to say, well, I can take out, I'm just going to write it out and I'll explain it. Like this, like that. So when I apply, here's my pointer. When I apply this to here, right, we are, and actually this should be like that. So when I apply this to here, I'm going to get that number because we're contracting, so that looks good. When I apply this to here, we're going to get that upper index mu back, okay? And we're going to get that change, okay? So this here is what we're calling our change in Euler-Lagrangian. And so what we do now is we give this a name. And this is T mu nu, which is the energy momentum tensor. Now, you might think, okay, well, hold up. Why are you calling this the energy momentum tensor? This looks nothing like energy or momentum. Well, again, like we've said, where here in Noether's theorem, if I wrote it down, yeah. When we shift what we've done is we've shifted, we've done this shift right here, right? And when we do this shift, if you remember, these are functions of time. So we're also doing a temporal shift here when we shift our coordinates, because again, these things are functions of time. And so, and you can see that here also, x mu covers time and space, right? Because these are 4 vectors. And so that's this, or that's why we're calling this an energy momentum tensor, is because we're conserving energy and we're conserving momentum, okay? And the energy momentum tensor, if you recall, or if you've seen it at all, you don't necessarily have to have seen it yet, you can sort of visualize it as a matrix, right? Like this. And then we have our T11, our T22, and our T33. And here we have T12, T13, or T21, T23, T3, and this this is 1 and 2. There's 16 components to our energy momentum tensor. This one corresponds to our energy and what's called an energy density. And we'll cover why. We'll understand that why this is the case later. These guys correspond to energy flux. These guys correspond to pressure. And these and these correspond to shear stress. Not shear. And what this looks like is that you have, since we're looking at fields again, what we have is this energy momentum tensor. It's a function of our space. And so what we have is we have pressure, we have an energy density, or we have a pressure at that point, we have pressures at that point in different directions. We have energy flux through that point. We have an energy density at that point, and we have shear stress at that point. And this tensor describes all of that. And we can go further here. We can talk about, we could say now, okay, so if dl is 0, if the change in our Lagrangian is 0, right? i.e. nothing changes about our Lagrangian, just like we've been talking about with Noether's theorem, then that means that d mu t mu nu a nu equals 0. Right, well, a nu is just a vector, so this means that t mu nu equals 0. So what does that mean, right? So I will go into another page here. So we have our d mu t nu equals 0. Well, what we can consider now is, say, our 0th component, where mu is equal to 0. If mu is equal to 0, then we have something that looks like this. So here I set mu equal to 0. So this takes out the temporal component of our tensor. Here I don't set it equal to 0, but instead I set everything else equal to 0. So these are the spatial parts of the tensor. Excuse me. And so if those equal 0, then we can say that equals di ti 0, like that. Because again, if I go back here, this here, 0, with 0 up here, where does that map to on our matrix? That maps to these values right here, right? So these are energy fluxes. And then with zeros down here, well, those are these right here. These are also energy fluxes, but we're looking at, actually, did I do that right? Yes. And actually, we're actually setting nu equal to 0. So if we set nu equal to 0, oops, that's more because, okay, that's where I was getting a little bit confused. I accidentally did not put that equal to 0. But nevertheless, what we have, okay, so what we have here is that this here is actually the energy density, right? The other ones, these are the energy fluxes, right? So we'll go like this, oops. So this is our energy density, and this is our energy flux. Right? So this is actually, what is this? This is actually corresponds to something that looks like this. Because di here, this di, this is just a derivative with respect to temporal locations, like this. And so what we can do here is this is the continuity equation, right? This here is the continuity equation. So what is that? What does this mean? This means that what if we were to derive, if we were to say that this here is the energy momentum tensor, based off of Noether's theorem and applying a space-time symmetry, we can recover our continuity equation for energy. What this means is that at some point in our field, here's our field again. At some point in our field, at this point we have an energy density, but we also have energy flux, and the energy density is equal to the amount of the negative or whatever of the not the negative, but it's equal to the amount of flux that enters or exits, right? So the amount of energy there at that point is equal to the amount of energy that's coming and going at that moment, at that point, right? So this is, we've recovered, upon pursuing this space-time symmetry, where we shift our space-time, we were able to show that the continuity equation is what comes out of that. Right, so we apply, again, we apply Noether's theorem. I'll go through this one more time. I'm pushing on 45 minutes, which is something I haven't really done yet, but keeping this all contained in one video, I think, is probably a good idea. So we've found out what the change in the Lagrangian is, okay? And we had the space-time symmetry we wanted to consider, okay? And then what we did is we did a bunch of math. We did a bunch of math down here. And we eventually came to this point where we defined this object right here in terms of our Lagrangian. We defined it as a tensor. We call it the energy momentum tensor, okay? And this energy momentum tensor, we found, corresponds to energy density at a point and energy flux going out of that point. And we were able to recover the continuity equation, okay? This was a big video. Again, I apologize for having gone over about 15 minutes or so here. Again, I do want to keep these videos relatively short. I think the next video is going to be shorter, right? So the next video, we're going to cover internal symmetries. And internal symmetries are, we're going to come to ideas like charge and stuff like that. And we're going to want to consider, I think, complex scalar fields. And then after that, we're going to get into the meat of chapter 5, or a big chunk of chapter 5, right? So we're still in chapter 4 here. The next video is going to be chapter 4 also, but then the following video is going to be chapter 5. Chapter 5 is where things are really going to come together, right? We're actually going to start talking about the Klein-Gordon Lagrangian and the Dirac Lagrangian and the Proca Lagrangian. That's where a lot of this is going to merge, because we've talked about Lagrangians, how they're related to internal symmetries, right? And once we say, okay, well, here's what our Lagrangian looks like, here's what our Klein-Gordon Lagrangian looks like, we can all of a sudden, we can derive our equations of motion, we can derive our any sort of continuity equations that might come out of them, we can derive symmetries within them by using Noether's theorem. Again, the idea is, once you have the Lagrangian is the picture, or the Lagrangian is the thing that we're always going to refer to, right? So if someone tells you, what is the internal symmetry that's associated with the Dirac Lagrangian, we're going to be able to do that, okay? And so I hope I've left you with something to think about at least. And if you like this kind of stuff, again, please visit my Patreon page. Please hit that subscribe button, or you can just keep on watching. So I'll see you guys in the next one. Bye.